Now I want to look at a nonlinear state space model, a generic one, and see how would we linearize this model in order that we would be able to use our linear systems techniques we'll be learning in the course. So remember that for a generic linear system we expect to be able to write x dot equals ax plus bu and y equals cx plus du. And we may have some initial conditions as well. So let's let delta x, delta y, and delta u be what we call deviations from the nominal trajectory. So then I can express my signal x of t is equal to some initial condition x0 of t plus delta x. So x0 of t is the operating range, or the operation point that I want to be at. And then delta x is just any difference from that operating point. So I can do the same thing for y of t as y0 of t plus delta y, and u of t is u0 of t from plus delta u. So again, I'm not rewriting this equation here in terms of x dot. I'm just giving a different way to express the signal x of t as two component signals. The nominating, or the nominal signal x0 of t, and then any deviations from that are delta x. So now I want to be able to approximate my function f of xu, which may be some nonlinear function, with a Taylor series. And so in order to do this, I'll get to use partial derivatives, because I may have a nonlinear function where f of x and u, the x terms may be multiplied by one another, or x terms may be multiplied by u's. And so I can't use just regular derivatives anymore. I need to use partial derivatives. Yay! Okay. So now let's assume that I have some function f of xu, and I'm going to write this function as its Taylor series equivalent, or actually it's a Taylor series approximation. So I take my operating point, f of x0 u0, so that gives me the first part of expressing this function. Then I'm going to add to it the partial derivative of the function f of xu with respect to x. And I'm going to evaluate that at x0 u0 and multiply it by the deviation x minus x0. So this is the first part of the derivative, but this is not enough to capture the whole signal. It would be if this was a linear system. I would just be able to take the partial, or just be able to take the derivative with respect to x. But I can't do that here because u may actually be multiplied by some of the x terms. So I also need to add the derivative, f of xu with respect to u, and evaluate that at x0 u0, and multiply it by any of the deviation from u0. So this is going to be multiplied by u minus u0. So now I have our original operating point, f of x0 u0, plus the first order term here. This is the first order term with respect to x, and the first order term with respect to u. So these three will be a pretty good but not perfect approximation. So I'm going to make sure that these higher order terms, I'm going to just assume that all of these go to 0. So if they don't go to 0, then my linear approximation will not be very accurate. And this is why, again, when we look at how we want a system to behave, sometimes we want to stay within a certain area of our nominal trajectory. So if we go outside that trajectory, our system model may not be valid anymore. So that, for example, you may have a system that looks a little bit like this, where you have a nice linear region and then suddenly it drops off. So you want to make sure that you always stay within this region right here, because if you ever get greater than a certain value, or greater than a certain value of x, now you're going to have a nonlinear response. So many times you'll see that this becomes an overshoot constraint. I want to make sure that my force never gets greater than such and such value, because if it does, then my system's not going to behave in the way that I expect. Okay, so when x is a vector, del f del x is actually a matrix. So we can write it as the following way. So here we have del f del x is equal to, and then my first, the upper left hand part, so element 1, 1, is delta f1 del f1 del x1, so it's some new function del f1 del x1, which is the derivative of f with respect to the first variable in the vector x1 of x and u. And I'll take this derivative for every term that I have of every term that I have of x, and take the derivative of this f with respect to each of those individual values. So that'll give me the first row of my matrix. And column-wise, I'm taking the derivative with respect to x1 of the function repeatedly. So now, as I build this out, I'm going to eventually have del fn del xn, which is going to give me the full matrix. So each one of these f terms, if we decompose x into a series of vector values, we're going to have basically f1, f2, f3, all the way to fn. So I take the first of those values, f1, take the partial with respect to x1 all the way to xn. That gives me my first column, and my first row. And for each column here, we're just always taking with respect to the column del x1. We're taking with respect to whatever the row value of the function happens to be. So this will become more clear when we do an example. But for now, just accept that the partial with respect to x is going to be a matrix if we have a vector for x's. So now we can do the same thing similarly for y as some function g of xu. Okay, where do we go from here? Well, now if we rewrite that x dot is equal to x dot 0 plus delta x dot, we can rewrite this in terms of the Taylor series expansion. So remember, x dot is equal to some function f of xu. So we've approximated f of xu as our operating point here, plus the first order term of x, plus the first order term of u. So we've approximated f of xu as 3 terms here. And we can do the same thing for y. So we take the operating point, g of x0, u0, and then the partial with respect to x times the deviation from x, plus the partial with respect to u times the deviation from u. So now we have something that's looking a little bit more like it could be a linearization point. So just remember, when we take del f del x, we get a matrix. So this value here is a matrix. This value here is a matrix. All of these values are matrices. So we're going to get something that now looks a lot like delta x dot, delta y dot. We're going to be able to express these as their own linear systems. So the deviation from our operating region is itself a linear system. So here we have delta x dot is equal to a times delta x plus b times delta u, and the same for delta y. So again, this is not for the entire system. This is for the deviation from our operating point that we get this linear system, where obviously a is equal to del f del x evaluated at the operating point, b is del f del u evaluated at the operating point, c del g del x, and d del g del u, again evaluated at the operating point. So this linear system, again, it's not the full value of what our system should be behaving at any point. It's only valid for the operating point that we've selected. So this gives us the linearization about an operating point for a state space model.